Hi, this is Axel.
This is Olaf.
And we're from PTB in Germany. Welcome to this short tutorial about the determination of absolute isotope ratios. We're going to give you a really brief overview on how to use gravimetric isotope mixtures to determine SI traceable isotope ratios. Therefore, let's directly start with the actual problem. There's no mass spectrometer on Earth that directly measures isotope ratios. Mass spectrometers will always measure signal intensity ratios instead. The actual problem now is that the measured intensity ratios differ more or less from the isotope ratios. The difference can be up to more than 10% in case of lithium, while it's below 1% in case of heavier elements like lead or uranium. Consequently, the signal intensity ratios are expressed, for example, in volt per volt, depending on the type of mass spectrometer you're using, while the isotope ratios are expressed in mole per mole, their SI base unit. This phenomenon as a whole is called instrumental isotopic fractionation, or short IIF. But the more common name is still mass bias, even though this name is not entirely correct. To convert the measured into the actual isotope ratio, usually a simple multiplication with a so-called correction or short K factor is done. Therefore, the problem is now to determine this K factor. The determination of the K factor can be done in several ways. Firstly, there are more traditional correction models from the TIMS time, like the linear, exponential, the power, or the Russell law. These models work more like approximations, and in the end, they do not yield SI traceable isotope ratios in most cases. The next group of methods are based on the use of SI traceable isotope reference materials. Among them, the use of a double spike, or the standard sample bracketing, or the combination of the standard sample bracketing with an internal normalization, like for example the exponential law, or the so-called optimized regression model, where, for example, the plasma power is varied during the measurement to yield the K factor. Now, using gravimetric isotope mixtures is the third method. Isotope mixtures have several advantages. They do not require a reference material or are restricted by any simplifying assumptions. In the end, the use of isotope mixtures will yield SI traceable isotope ratio. This way, this is the primary method. But how does it work? Copper as a two-isotope system is a really simple example. You will need two starting materials, A and B, each one enriched with respect to one of the two isotopes. In this case, it's 63. In this case, it's 65. Now you mix certain amounts of A and B using a balance so that you know the masses MA and MB. After properly equilibrating the resulting mixture, the only thing you have to do is to measure the signal intensity ratios in A, in B, and in the mixture AB. The K factor is then simply a function of the two masses, MA and MB, and of the three signal intensity ratios that still differ from the wanted isotope ratios. You have to keep this in mind. This function is usually derived from the definition of the isotope ratio RAB in the mixture, the isotope ratio, not the signal intensity ratio. All amounts N and the amount fractions x can then be replaced using the well-known masses and the signal intensity ratios, yielding in the end the equation in the blue box that allows for the calculation of the K factor directly from the intensity ratios, the masses that were mixed, and the molar masses of the isotopes here in the beginning of the equation. The resulting K factor can then be used to convert the intensity ratio into the SI traceable isotope ratio. This is now another example. It's from the Avogadro project, where we investigated silicon for nearly the last 2 decades. Since silicon consists of 3 isotopes, the problem becomes a bit more complicated. From the 3 enriched starting materials, which you can see here, you can prepare 3 independent blends. But to calculate the necessary 2 K factors, only 2 of the blends are needed. The third blend can be used, for example, to check for plausibility of your results. In case of a 3-isotope system, like the already mentioned silicon from the last slide, the equations to calculate the K factors become more complex. But they still can be written down explicitly, like you can see here. The mathematics originally derived in the Avogadro project was successfully applied for the characterization of several magnesium isotope reference materials. But what happens when the number of isotopes is 4 or even larger? This was until some years ago the territory of numerical or iterative mathematics, and also unwelcome simplifying assumption had to be made. But since 2020, explicit solutions for any number of isotopes are available, accessible through an Excel application called GIMIC. Another tool based on Monte Carlo methods called ANCORC helps to calculate the uncertainties associated with the K factors and the resulting isotope ratios. Now let's look at a really strange example. Is the gravimetric mixture method restricted to the determination of absolute isotope ratios? No, it's not. In case you already know the isotope ratio, you are free to rearrange your equations to your liking. In the framework of the Avogadro project, we used gravimetric mixtures to determine the molar mass of silicon, which was extremely high enriched in the 28 silicon isotope. Due to this high enrichment of the 28 silicon, no reasonable silicon concentration allowed the measurement of all 3 silicon isotopes at the same time. Therefore, we used a certain method that we called virtual element IDMS. The basic idea of this method is to completely ignore the 28 silicon and imagine a so-called virtual element that only consists of 29 silicon and 30 silicon. Now we were able to do IDMS with this virtual element. The preparation of a gravimetric mixture enabled us to calculate the mass fraction of the virtual element in the bulk of the silicon. From this mass fraction, the amount fractions of all 3 isotopes could be reconstructed. And from these eventually the molar mass that we wanted to determine. The equation to calculate the molar mass combines the mixed masses of the starting materials of the silicon isotopes and the isotope ratios in the blend with the molar masses of the isotopes. This really strange method can be applied whenever a really high enrichment and a high purity of the sample coincides. Let me summarize. When you want to determine isotope ratios, especially Si traceable ones, you have to be well aware of the fact that mass spectrometers do not measure isotope ratios directly. You have to correct the measured signal intensity ratios for the unavoidable instrumental isotopic fractionation. To do this, you have to determine the K factor. This can be done in different ways. From the methods available, the most time-consuming and costly approach is to prepare gravimetric isotope mixtures. But this is the most sophisticated method and virtually the only one yielding Si traceable isotope ratios. Thank you very much for your attention, and you will find more details about the things we covered in this tutorial when you follow the links on the respective slides. Okay, that's it.